So again, we're in chapter 2, which we're focusing on matrices and matrix operations and stuff. But before I do that, there was one problem that I knew people were going to complain about, so I had you set up for it. So this was on the test, so here it is. We're going to work together on this thing. I want you to solve this system. Now, read the directions, because this is the kind of stuff that I put on the test. So it's very word-oriented. First thing I want you to do is this. 3 points. Here's a system of equations. x1 plus 4x2 minus 8x3 equals 7. Negative 3x1 minus 7x2 plus 9x3 equals negative 6. And 2x1 plus 6x2 minus 10x3 equals 8. I want you to write it as a matrix equation. To write it as a matrix equation, you have the coefficient matrix, okay, which would be 1, 4, negative 8, negative 3, negative 7, 9, 2, 6, negative 10. This is your matrix A, multiplied by your unknown x vector, which would be the x1, x2, x3, a vector in R3, because there's 3 components, and it is equal to what we say is called the B vector. This is your constant vector, 7, negative 6, 8, also a vector of R3. Does that make sense? This is just writing the system of equations as a matrix. Now, I know, again, I am trying to do a little bit of chapter 2 here. When you want to solve this guy, you typically want to write it as an augmented matrix. But if I ask you to write it as a matrix equation, A times X equals B, coefficient matrix, your X vector representing the variables, equals the constant B. Okay? Now, solve this system of equations for me, please. Now, if I wanted to solve this thing, and based on what we've covered so far, don't worry, we're going to learn about new ways of solving this stuff in chapter 2. But right now, still focusing on what we learned in chapter 1. Chapter 1 was large, it had 10 sections in it and stuff. I would augment this matrix. This would be 1, 4, negative 8, negative 3, negative 7, 9, 2, 6, negative 10. Augment with that 7, negative 6, 8. What's your first move? This is the game we want to play. I even put some problems on there. I'm only going to give you 3 moves to turn this thing in row echelon form or something like that. Again, I put a lot of definitional stuff. You need to know reduced echelon form, row echelon form, and non-forms and stuff like that. So here, I would take that 1, sweep down and kill off that negative 3. That means 3 times row 1 added to row 2. And whatever you add is what you replace. So add row 2, replace row 2. And then I'm going to sweep down and do negative 2 times row 1. Add it to row 3, replace row 3. That's going to give me 1, 4, negative 8, augment with 7. 3 times negative, so 3 times 1 is 3 plus negative 3 is 0. That's the point. 3 times 4 is 12. 12 minus 7 is 5. 3 times negative 4, 3 times negative 8 is negative 24. And negative 24 plus 9 is negative 15. And 3 times 7 is 21 minus 6. 21 minus 6 is 15. Now let's sweep down and kill off this 2. Negative 2 times 1 is negative 2 plus 2 is 0. That was the point. Negative 2 times 4 is negative 8. Negative 8 plus 6 is negative 2. Okay. 2 times... negative 2 times a negative 8 is a positive 16, and 16 minus 10 is a 6, and 7 times negative 2 is negative 14, plus 8 is a negative 6. So far, so good. Making my moves now. What's your next move? What would you do? Didn't hesitate. You should jump out immediately. This is a time issue. Yeah. And how are you going to do that? 1/5 times row 2, replace row 2. Let's make him a pivot. So this is 1, 4, negative 8, augmented with 7. Now it's going to become 0. 1/5, 5 is a 1, making him a pivot. Negative 15 divided by 5 is a negative 3. 15 divided by 5 is a positive 3. And then 0, negative 2, 6, negative 6. What's my next move? sweep down. 2 times row 2 added to row 3, replace row 3. 1, 4, negative 8, augment 7, 0, 1, negative 3, 3, and then, here we go, 0 times 2 is 0 plus 0 is 0, 2 times 1 is 2, plus negative 2 is 0, 2 times negative 3 is negative 6 plus 6 is 0, and 2 times 3 is 6 plus negative 6 is 0. I get a row of zeros on this one. Does that make sense? If this was a number, this last column was a number and not 0, what would the answer have been? Inconsistent, and you're done. But this one is, so we keep going. I got one more move to make. What's my last move? Sweep up. That would be multiply negative 4 times row 2, add it to row 1, replace row 1 with that. This would give me 0, 0, 0, augment 0 on the bottom. 0, 1, negative 3, 3, and then 1. 0 times negative 4 is 0, plus 1 is still 1. Negative 1, excuse me, negative 4 times 1 is negative 4 plus 4 is 0. That was the point. Negative 4 times negative 3 is 12. And 12 plus negative 8, 12 minus 8 is 4. And then last, negative 4 times 3 is negative 12. Plus 7 makes it a negative 5. Agreed. This is now in reduced row echelon form. You should recognize that. I want you to write the answer in parametric vectored form. So how do I do that? I'm going to go back and rewrite these as equations. This becomes x1 plus 4x3 equals negative 5, and x2 minus 3x3 equals 3. How do I write it in parametric vector form? You solve for the pivots. This means x1 is equal to negative 4x3 minus 5. x2 is equal to, add 3x3, that'll be plus 3x3 plus 3. And x3 is equal to who? x3, because that is your free variable. Okay? So, now to write it in parametric vector form, this leaves me with my answer, writing in vectors. The vector x1, x2, x3 is equal to, bracket, negative 4, 3, 1 times x3 plus the constant vector negative 5, 3. There is no constant down here, so that would be 0. Does that make sense? There's my answer. You good so far? Okay, and I'll put it back up here so you can see this thing. I want you to write down for me 3 points here. What would the coefficient matrix be? Again, this is just terminology here. What is the coefficient matrix? That is the matrix that is the numbers in front of your variables, right? So what would be my coefficient matrix? This is 1, 4, negative 8, negative 3, negative 7, 9, and 2, 6, negative 10. That is the coefficient matrix. It's just the numbers in front. And if you come down here, it's this matrix A right here. That's called the coefficient matrix. Again, I'm after that terminology aspect of it. Does that make sense? So now, my next question is this. Check to see if the vector negative 5, 3, 0 solved this system of equations. How do I figure that out? Remember, we had AX equals B, right? We're saying if this solves the equation, I can multiply A, which is this matrix here. This is actually the A matrix. 1, 4, negative 8, negative 3, negative 7, 9, 2, 6, negative 10. I'm going to multiply it times this V vector, which is negative 5, 3, 0. And let's see what we get. Remember how to multiply matrices. Again, emphasizing this. We're also emphasizing this in Chapter 2, but we also emphasize it in Chapter 1.1 and 1.2 and stuff. Row times column. 1 times row by column. 1 times negative 5 is negative 5. plus 4 times 3 is 12, plus negative 8 times 0 is 0. So it is negative 5 plus 12. You see how I'm keeping up with this. I get 7. Second row, first column, negative 3 times negative 5 is 15. Plus negative 7 times 3 is negative 21. So that's 15 minus 21, and 9 times 0 is 0. So 15 minus 21 is a negative 6. And then third row, first column, 2 times negative 5 is negative 10. Plus 6 times 3 is 18. So it's negative 10 plus 18. And last, negative 10 times 0 is 0. And negative 10 plus 18 is 8. That is my solution. Now, we were talking about, okay, put it right here. We were talking about being able to solve this system of equations, or more or less, when I write it as a system of equations, we're talking about solving this guy. Did this vector, negative 5, 3, 0, solve this system of equations? When I plugged in for x, did I actually get these answers? 7, negative 6, 8? Yes, I did. So the answer for this is yes, it did solve it. If I did not get in 7, negative 6, 8, then the answer would have been no. That makes sense. Got a question for you. What is the homogeneous solution to this system of equations? What does homogeneous solution mean to you guys? A times x is equal to who? 0 vector. So if you want to solve this guy, you can take 1, 4, negative 8, negative 3, negative 7, 9, 2, 6, negative 10, augment it with 0, 0, 0, and then I'm just going to help you guys out. When I do the reduced row echelon form on this guy, okay, what do we end up getting here? Well, I've already done the reduced row echelon form on this guy when I did, this other paper right over here. I did reduced row echelon form, I got this thing here, okay? I got 1, 0, 4, 0, 1, negative 3, 0, 0, 0, but when you're homogeneous solution, you set it equal to 0, 0, 0, which means we end up getting the equation x1 plus 4x3 equals 0, x2 minus 3x3 equals 0. If we write the answer in parametric vector form, what do we get? We end up getting x1 is equal to negative 4x3, x2 is equal to a positive 3x3, and x3 equals who? x3, because that is your free variable, right? So as a parametric vector form, you get x1, x2, x3 is equal to negative 4, 3, 0 times x3. That is the homogeneous equation. This is the point that I was trying to make and mentioned in class a couple of times, but here's the deal. When you look at the solution, you remember that AX equals B equation that we had before, which was this 1, 4, negative 8 times negative 3, negative 7, 9, 2, 6, negative 10. You multiply it times x1, x2, x3, and we were setting it equal to the B equation, which was your 7, negative 6, 8 equation. This was this answer right here. When we look at that answer right there, you get this. What was x1, x2, x3 equal to? It's actually the homogeneous equation, which we just did, which was this negative 4, 3, 0 times x3 plus what we call the particular solution. What was my particular solution on this guy? It was, we checked it, did this vector actually work? It was that negative 5, 3, 0 actually worked on this guy. Does that make sense? Homogeneous, which is coming from this answer, plus this particular vector that solved the entire equation, those two answers put together. And if you go back to the part number 2, that's exactly what we got. Answers always show up in two parts. The free variable part is actually the homogeneous solution, and any other constant vector is the particular solution. And that's what I meant by when you can take two parts of the answer and put them together. Yeah. Equal to, wait a minute, x3 should be 1. Thank you. That's because I'm doing this thing at 90 miles an hour. x3 equals x3. Thank you. And if you look at it, yep, it should be a 1. So thank you. You should be equal to 1. That is my fault because I was going way too fast on this guy. Thank you. But does that make sense, though? And that's what I meant by, on that particular problem, I made you solve the homogeneous. I made you check to see a particular solution. And to get the actual general solution, you just take the homogeneous plus particular. And then I even put in parentheses, just add the homogeneous answer to the particular answer, and you got your answer. So I was trying to help you guys out to remind you of that, but trying to show you how the answers, you can look at answers of these systems of equations, and they're breaking into two camps, particular solutions and homogeneous solutions. All right, let's pick up where we left off last time, which is back in section 2.1. We were looking at, and again, just to remind you, we did this problem last time, so this is the right off of our notes from our last video and stuff like that, our last class. We talked about the definition of transpose, okay? And transpose, remember, was taking rows of a matrix, turning them into columns. So you basically start with a matrix, and you look at all the rows, and just rewrite them as columns, and that new matrix is going to be called A transpose. And we had some properties that A transpose, you get right back to where you started from. If you turn rows into columns and turn those columns back into rows, you get right back to where you started from. A plus B transpose would be the same thing as A transpose plus B transpose. If you take a scalar, which is some constant, multiply it times a matrix A and transpose it, that's the same thing as just go ahead and taking the matrix A and transposing it, and then multiplying it by the scalar. Transpose won't matter. But here's an extra special property. When you take a product of A times B, and then you do the multiplication of the two matrices and transpose it, that's the same thing as, it reverses, B transpose times A transpose. You have to flip the order. B transpose, then times A transpose, and that'll give you the same answer. And again, we did a bunch of problems on how to multiply matrices and stuff. And down here, we did the actual transpose, which was turning the rows into columns. Here it is, turning the rows into columns. So there we go. Again, just to pick up where we left off last time. All right. So I didn't quite get to these guys here. So I want to pick it up with these examples here. Just again to practice, pick up where we left off and keep going. I would like you to take the transpose of the matrix 0, 2, 1, 1, negative 4, 0. What would my answer be? Well, what size matrix is this to begin with? Just again practicing. This is a 3 by 2. So when you transpose, turn rows into columns, what are we going to end up getting? A 2 by 3. And so the row becomes a column, 0, 2. The row becomes a column, 1, 1. And the third row becomes the third column, negative 4, 0. And there's my answer. Transpose. Again, we're talking about, again, just to practice our classic matrix multiplication. Remind you, to multiply matrices is this row by column, and that becomes the row column entry and stuff. So if you got a matrix A, which is M by N, and you multiply it times a matrix B, which is N by J, the only way you can multiply these guys is the number of rows by columns. The columns on the first matrix has to match up to the rows on the second matrix. If you got that, you can multiply them. If you do not have that, the answer is cannot do. It's the wrong size. So, and when you do this, multiply A times B, and the number of columns on the first matrix match the number of rows on the second matrix. They match up, cancel, and you're left with an M by J. That'll be an A times B, M by J matrix. So if I let A be equal to the matrix 1, 2, 3, 4, because I have no imagination, and I let B be equal to the matrix 2, 0, 6, negative 1, 4, 1, what would A times B? Well, first off, always check my sizes. This is 2 by 2, this is 2 by 3, So this matches up and cancels. That's the most important thing. So I can multiply this matrix. So now I'm going to do row by column. 1 times 2, which is 2. 2 times negative 1, which is negative 2. 2 plus negative 2 is 0. First row, first column position would be 0. First row, second column. First row, second column position. 1 times 0 is 0. 2 times 4 is 8. 0 plus 8 is 8. And then first row, third column position. First row, third column position. 1 times 6 is 6. 2 times 1 is 2. 6 plus 2 is 8. Now, second row, first column position. 3 times 2 is 6. 4 times negative 1 is negative 4. 6 minus 4 is 2. Second row, second column position. Second row, second column. 3 times 0 is 0. 4 times 4 is 16. 0 plus 16 is 16. And then the second row, third column position. Second row, third column position. 3 times 6 is 18. 4 times 1 is 4. 18 plus 4 is 22. And there's my resultant done by hand. Does that make sense? Again, practicing is the key here. So let's do another one. Multiply these two matrices together. Now, I know we all have calculators, and they got the little buttons on them, and they work very nicely here. But, and I'll even show you how to use the calculator. I don't have a problem with that. But I want you to be able to do it by hand first. So, I got the matrix 2, 5, 2, negative 4, 7, 1, multiplied by the matrix negative 1, 2, 1, 0, negative 4, 1. What size matrix is this guy? This is a 3 by 2. 3 rows, 2 columns. What size matrix is this? 2 by 3. 2 rows, 3 columns. So what is my resultant matrix going to be? It's going to be a 3 by 3. Does that make sense? Rows by columns. So here we go. First row from first column. First row, first column position. 2 times negative 1 is negative 2. 5 times 0 is 0. Negative 2 plus 0 is negative 2. First row, second column position. 2 times 2 is 4. 5 times negative 4 is negative 20. And negative 20 plus 4 is what? Negative 16? You can see if you do this in your head, it's real easy to make a bonehead careless error. Just be careful. First row, third column position. 2 times 1 is 2. 5 times 1 is 5. 2 plus 5 is 7. Second row, first column position. 2 times negative 1 is negative 2. 4 times 0 is 0. Negative 2 plus 0 is negative 2. Second row, second column position. 2 times 2 is 4. Negative 4 times negative 4 is 16. 4 plus 16 is 20. Second row, third column position. 2 times 1 is 2. Negative 4 times 1 is negative 4. 2 plus negative 4, 2 minus 4 is negative 2. Third row, first column position. 7 times negative 1 plus 1 times 0. 7 times negative 1 is negative 7. 1 times 0 is 0. Negative 7 plus 0 is negative 7. Second row, second row, second column position. Third row, second column position. Third row, second column position. 7 times 2 is 14, plus 1 times negative 4 is negative 4. 14 plus negative 4 is 10. And then second row, third column position. 7 times 1 is 7, plus 1 times 1 is 1. 7 plus 1 is 8. There's my result. Again, it takes practice, and it is easy to make careless errors. So if you wanted to do this on your calculator, you're more than welcome to double check your work, but remember there is a time limit on this stuff, so remember that. So you want to kind of do it first, show your work, and then go back and double check yourself on things. All right, so this matrix was 3 by 2. Call this matrix A. 2, 5, 2, negative 4, 7, 1. Second matrix, edit B. This matrix is 2 by 3. 2 by 3. This is negative 1, 2, 1, 0, negative 4, 1. So when you hit enter, it goes to the, you read this row-wise, just to let you know. And then second quit, and I always check my matrices. Matrix A, make sure I copied it down correctly. Matrix B, second B, just put the names at the home screen. Negative 1, 2, 1, 0, negative 4, 1. And now, matrix A times matrix B. And when I hit enter, and I should get this matrix. Negative 2, negative 16, 7, negative 2, 20, negative 2, negative 7, 10, 8. I feel real good about my basic arithmetic skills. But it's easy to do it on the calculator to double check yourself. And I don't have a problem with that, but you have to be able to show your work with a lot of this stuff. So here we go. Now with matrix multiplication, I mean, most of that stuff I'll have to admit I do in my head. So now, when it comes to properties, here is our properties of addition of matrices and scalar multiplication. So, all right. I'm breaking this up into little sections here. So let me blow this up a little bit so you can see this in the back here. All right. Properties of addition of matrices and scalar multiplication. Now, to be able to add matrices, they got to be the exact same size. So A here is an m by n, B is an m by n, R and S are going to be scalars, constants. So A plus B is B plus A. That is called commutativity. Getting you used to more definitional terminology. Doesn't matter what order you add matrices in, you get the same thing. A plus B is B plus A. Okay? And A plus B, with parentheses around it, plus C is the same thing as A plus, parentheses, B plus C. When I move parentheses around, that's called associativity. Under addition, matrices, doesn't matter about associativity. You can take whatever order you want to. Add the first two guys, then add the third one, or add the last two guys, and then add the first one. You have something called a zero matrix, which would have to be the same size, which is a zero matrix, is the zeros in every entry. And then you take A plus 0, you get A. How about scalar scalar multiplication and addition with matrices? If I multiply scalar R times A plus B, you can distribute R and get AR plus AR times A plus R times B, and it's going to be the same thing. And so listen up. You can distribute the scalar, which means I can multiply through by the scalar and drop my parentheses. Or if I flip it up and I have R plus S, two scalars being added together, then all that multiplied by matrix A, you can actually distribute matrix A and get R times A plus S times A. You can distribute scalars or in the front, or you can distribute the matrix A in the back and still get the exact same thing. And again, scalar multiplication doesn't matter about order. So R times S times A is the same thing as multiplying R times S, then multiplying it times A. Okay? Now, properties of matrix multiplication. So here I have A, B, and C of proper size. Now, what do I mean by proper size? So to be able to multiply A times B, A's got to be M by N, B's got to be N by somebody. And if you got matrix B times C, that B's going to have to be N by somebody. Let's say W. Then C's got to be W by somebody else, because the the columns on the first matrix have to match the rows on the second matrix being multiplied. But if you have that, then A times B times C is the same thing as A times B times C. Again, associativity. I can move parentheses around this multiplication. It doesn't matter what order. As long as you can multiply the matrices, they're the right size. It doesn't matter what order you take these things in. But now with distributive, you got A matrix A times B plus C. Now B and C have to be the same size to be able to add them. And then you'll be able to multiply them. The columns on A have to match up to the rows on B and C here. But if you can do that, A times B plus C is the same thing as AB plus AC. And B plus C times matrix A in the back will be B times A plus C times A. We call this right distribution. Matrix A on the right is being distributed. Or left distribution. A is on the right and you're distributing through the B plus C. So you have, basically right distribution. A is on the, so you're distributing through the right, or you're distributing through the left is basically the terminology here. And again, scalar multiplication, R times matrix A times B is the same thing as multiplying R times A, then multiplying it times B. Or if you really want to, if it makes it easier for you, take R, multiply it times matrix B, and then multiply matrix A times matrix RB. You'll get the exact same answer on all three of these guys. Now, we also talked before about this idea of an identity. Identity means this is a matrix that you multiply by another matrix, and you get the other matrix right back again. This guy is going to have a real special look. The identity matrix is going to be a square matrix, so it's going to be the same rows as columns. And so here we put the little subscript here. So A is m by n. This I, which is m by m, you can multiply it times A, which is m by n, so the rows match with the columns type thing here, so you can multiply them here. But A times matrix I with m times A is the same thing as m. You'll get A back again, m by n. But that'll be the same thing as A times IN. If A is m by n, you can only multiply on the right an n by n matrix to make sure the columns match up to the rows and stuff. And again, the identity matrix is this guy here. So if I just do IN, this would be an n by n matrix with 1, 0, 0, 0, dot, 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 0, 1, 0, dot, 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 0, 0, 1, 0, dot. And you get all the way down to 0, 0, dot, 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 1 right there. So you get ones on the diagonal and zeros off the diagonal. This is your identity matrix, and it's square, so the rows match up to columns. This is the matrix you multiply by to get the other matrix back again. Now here's your problem with matrices. They do not commute in terms of multiplication. One, you could have an issue with size. If you got 3 by 2 and you multiply that by 2 by 3, that works. But if you flip it up, it may not work, okay? So the order matters about the matrices. So in general, matrix A times B does not equal matrix B times A. There are a few examples that I can come across that I can rig the matrix that it works. But in general, this doesn't work. So matrix A times B does not equal matrix B times A. Order matters. Who's the guy in the front? Who's the guy in the back? And the reason for that is this row by column. If you switch it up, you're now working with columns and with the rows, and they don't match up and stuff. So an example here would be this. This matrix right here is what? This one is a 2 by 3. 2 rows, 3 columns. This one is a 3 by 2. What is my answer to this guy? Just in general, what size would he be? 3 by 2 times, 2 by 3 times a 3 by 2. What do you get? 2 by 2, all right? But if you switch this up, now this is going to be a 3 by 2 times a 2 by 3. We can multiply it, but what size matrix would this guy be? 3 by 3. And you can clearly see, even without multiplying it out, they're not going to be the same size. So they're not going to be the exact same matrix. Does that make sense? So, but even if they were the same size, let me show you. This is matrix A, this is matrix B, this is matrix B times matrix A. Let's take a look at what we get. Again, this is in general. So, 2, 3, 0, 1 times 0, negative 1, 1, 2. Row by columns. 2 times 0 is 0 plus 3 times 1 is 3. 0 plus 3 is 3. 2 times negative 1 is negative 2. 3 times 2 is 6. Negative 2 plus 6 is 4. 0 times 0 is 0. 1 times 1 is 1. 0 plus 1 is 1. 0 times negative 1 is 0. 1 times 2 is 2. 0 plus 2 is 2. So I get the matrix 3, 4, 1, 2. Now let's switch it up. Let's do B times A. Row by columns. 0 times 2 is 0. Negative 1 times 0 is 0. 0 plus 0 is 0. 0 times 3 is 0. Negative 1 times 1 is negative 1. 0 plus negative 1 is negative 1. 1 times 2 is 2 plus 3. 2 times 0 is 0. 2 plus 0 is 2. And then row by column, 1 times 3 is 3, 2 times 1 is 2, 3 plus 2 is 5. And you'll see that these are definitely not the same matrix. So in general, A times B does not equal B times A. You get two different kind of matrices out of that. On occasion, I can rig them up, that I can make these guys equal, but these guys are gonna be very special type of matrices to be able to do that. Most of them, in general, cannot. So, if you ever have this, matrix A times B is equal to matrix A times C, this will not always imply that B is equal to C, because you have problems with that idea of multiplication stuff. Also, and here's another property that gives you issues in terms of your classic algebra. In the old days of algebra, if I have two things multiplied together equal 0, either the first guy was 0 or the second guy was 0. We do that when we have quadratics. I ask you to solve x squared minus x minus 20 equals 0. Well, you factor it. That becomes x minus 5 times x plus 4 equals 0. You set each factor equal to 0, and you get x minus 5 equals 0, x equals 5, x plus 4 equals 0, x equals negative 4. And you get your solutions. That's called a property of 0. That's with integers. It doesn't work with matrices. So if I ever have A times B, A matrix A times matrix B, and that's equal to 0, I cannot automatically imply that the first matrix is equal to 0 or the second matrix is equal to 0. Okay? And I can rig this up where with these rows and columns and stuff like that, I can have a bunch of non-zero matrices, but I rig it up when I do row by column that everybody completely kills themselves off and I get a bunch of zeros out of the thing. But the first two original matrices were not zero to begin with. So these are some interesting properties about matrices, how to multiply them, and the properties of zeros that do not work, and the idea of matrices do not commute. A times B does not equal B times A. Yeah.
So for the first property at the end where you said matrix A times matrix B.
Yeah. It's equal to matrix A times matrix C.
You're saying that does not mean that matrix B is an equal to matrix C. Is that,
Yeah.
what was the reason of that?
Why does B not equal to C? All right. Okay, a couple of different reasons. I mean, because of this interesting row by column, I can rig this stuff up to make sure it doesn't work. So I know what you're thinking, but do you believe part B on this thing? If I have two matrices multiplied together that's equal to 0, will that automatically imply the first matrix was 0 or the second matrix was 0? Well, I can give you an example of that, like, 0, 1, 0, 0 times 1, 0, 0, 0. Okay? Well, hold on, if you don't believe me, I'll make up something very simple. I can make them more elaborate, but it caught me off guard here. 1, 0, 0, 0 multiplied by 1, 0, 1, 0. Let's do that. No, let's see, row, no, it's got to be a 0 there. Row. All right. Is this the zero matrix? No. Is that the zero matrix? No. All right, let's multiply. Row by column. What 0 times 1 plus 1 times 0? Yeah, 0. 0 plus 0 is 0. Row by column. 0 times 0 plus 1 times 0 is still 0. 0 times 0, 0 times 1 is 0. 0 times 0 is 0. 0 plus 0 is 0. 0 times 0 is 0. 0 times 0 is 0. 0 plus 0 is 0. So, not 0 matrix. Not the 0 matrix, but the 0 matrix. All right? It's very simple. I can do much more elaborate stuff, but there it is. I got two non-zero matrices multiplied together that's equal to 0. Now, here's the problem. If you say A times B equals A times C, right? That would also mean that A times B minus A times C is equal to the 0 matrix, right? I can factor out that A matrix. That would be A times B minus C has got to be equal to 0. But A, no, that's not the 0 matrix. Well, does that imply that B minus C has got to be equal to 0? We just proved up here, no, they don't have to actually be equal to 0. And if they're not equal to 0, then B will not be equal to C. So I can show you that as well. So there's a general proof, if you will, but very, very basic. Does that make sense? So that's why, just because A times B is equal to A times C, I cannot guarantee that B equals C. All right. over here. Talk about section 2.2 here. Section 2.2, we're going to be focusing on invertibility. And we got enough more, and I warned you guys about this, so just get used to it. Fancy words for it. An invertible matrix and what that actually means. So, an n by n matrix A. First off, n by n means what? We are now restricting ourselves to looking at what we call square matrices. Okay? N by n. So, n by n matrix A is said to be invertible if and only if there exists an n by n matrix C such that C times A is equal to A times C, which is actually equal to the identity I matrix. And the way I want you guys to look at the identity matrix is under multiplication, we have something called multiplication, the multiplicative identity. Multiplicative identity. It's 1. What's 1 times anybody? Itself, 1. But in matrices, that idea of 1 with regular numbers, complex numbers or real numbers or whatever, is the same thing as what this identity matrix I is going to be. But identity matrix have to be square. So when we put the little subscript here, n, that's going to be n by n. But A is n by n, C is going to be n by n. When I multiply C times A, I get the identity. 1's on the diagonal, 0's off the diagonal. Okay? But that'll be the same thing as A times C. So, we talk about a left identity and a left inverse and a right inverse. We talk about that kind of crap when it comes to non-square matrices. Our focus is going to be on square matrices. So the left inverse and the right inverse, they're going to be the same exact guy. You multiply them on the left, so this is one of those rare occasions that matrix C times A will be the same thing as matrix A times C, and you're going to get the identity. 1's on the diagonal, 0's off the diagonal. This is your classic identity matrix. IN is equal to 1's on the main diagonal, 0's off the diagonal. This is the identity matrix, n by n. Remark, C is uniquely determined. There's only one identity. You don't get to do multiple identities on this stuff. There's going to be only one identity with this stuff, okay? And he's going to, so every matrix A, if, keyword here, if it has an inverse, and not all matrices do, but if it has an inverse, it's going to be unique to that particular matrix, okay? So, what would a matrix that doesn't have an inverse? Hey, here's one, the zero matrix. Zeros, rows, and columns, nothing but a bunch of zeros. What do I need to multiply that matrix by to be able to get 1's on the main diagonal? I don't care what you multiply 0 by, you're going to get pretty much 0 on that thing. So you'll never get the identity. So there's an example of a matrix that's not invertible. There's lots of matrices that are not invertible, okay? So here we go. In fact, there is a B such that B times A equals A times B equals the identity matrix. Then B is equal to B times the identity matrix, which is equal to A times B, so A times AC, which is equal to B times A times C, which is equal to I times C equals C. Oh, what are you talking about, Dr. Taylor? Okay, let me explain. What does the word unique mean to you? There's only one and only one. So, if I told you up here, A has an inverse, he's called C. So we know that A times C is equal to C times A, which is equal to identity matrix. If I say there is another B matrix that's the inverse of A, in fact, if there is another B matrix such that B times A equals A times B equals the identity, remember I just gave you that C times A and A times C equals the identity. I'm going to show you that there's not two of them, there's only one. So watch this. B, which clearly is going to be equal to B times the identity. You can always multiply by identity, you get yourself right back again. But the identity can be replaced with AC, so B times AC, that's called substitution right there. And remember, in terms of our properties, we can move parentheses around. So B times AC is the same thing as B times A times C, but B times A we just said was the identity. And the identity times C gives me C back again. So what have you just proved? B is actually equal to C. So you may say there's two of them, but if they're equal to each other, there's only one, aka there's unique. And matrix C is called the inverse of A, and it's going to be denoted by A with a little minus 1 on top of it, the inverse notation. So we don't talk about him being C. And once we have identified the matrix A inverse, we're going to denote him as A with a little minus 1 subscript or postscript, A inverse. This is the A inverse. So you end up getting A times A inverse is equal to A inverse times A, because there's only one of these matrices here, and that gives you the identity matrix. All right, so, perfect. Definition. Matrix A is invertible. And here's a new word for you, and it's awful, but enjoy. Non-singular. Non-singular in the annals of matrix multiplication and linear algebra. Non-singular means it is invertible. All right, so let me just dive into this in just a second here. So invertible, you've got a matrix, it's got to be square. That is invertible. We're going to call it non-singular. So what do you think we're going to call a matrix who is not invertible? Don't hurt yourselves. Go. Singular. Okay, good. All right, so this is just the words. And I've always, when I took linear algebra when I was back at state, I always thought that was backwards. I always thought like, non would be like no, so it's not, exact opposite. Non-singular means it's actually invertible. Singular means it's not invertible. Just run with the definitions. I didn't make the definitions, I just reported them. So, invertible is non-singular, which means if there exists a matrix B such that A times B equals the identity, and B times A equals the identity, A must be square, then that B will be equal to A inverse, okay? Now, how do you find these elusive inverses? Well, there's one major way, an algorithm, but there's a special case. If you happen to have a 2-by-2 matrix, there's a fast way of getting the inverse, and that is this. Special 2-by-2 formula. It says this. If A is the generic form, A, B, C, D, no imagination, A, B, first row, second row, C, D. The inverse of this matrix, A inverse would be equal to A times D minus B times C times this matrix. D, negative B, negative C, A. So let me write this formula down for you so you can, I wrote down the formula, but here we go. It is A, B, C, D. Let me talk about what A inverse is going to be. There's a scalar constant you pull out front. You multiply the main diagonal minus the off diagonal, okay? A times D, and it's going to be 1 over. A times D, you do the main diagonal first, minus the off diagonal, B times C. That becomes the scalar out front. Now, what do you do with the actual matrices? See, this is your matrix, A, B, C, D. The main diagonal, switch the positions, switch the main diagonals. This was AD on the main diagonal, it becomes DA. Just switch the positions. The off diagonal, you just negate. Negative B from B, make it negative B, C, make it negative C, and that actually ends up becoming the inverse matrix. That's the pattern. Does that make sense? So, if I give you this, so here's my example down here, just want to show you. I got 1, 2, negative 3, 5. This is A. What would A inverse be equal to? Okay? So the first thing I'm going to do is I'm going to do 1 over main diagonal. 1 times 5 minus off diagonal. 2 times negative 3. Does that make sense? Main diagonal minus off diagonal, and it's 1 over that. Times, and what was my pattern? Basically, main diagonal, switch positions. So this is a 1, 5, so this becomes a 5 and a 1 on the main diagonal. The off diagonal, switch their signs. This was a 2, it becomes a negative 2. This was a negative 3, it becomes a 3. Make sense? Now, clean them up. We actually want to see what the matrix looks like. So A inverse actually is, let's see here, 5 times 1 is 5. 2 times negative 3 is negative 6. 5 minus negative 6 is what? Minus negative is plus 6. 5 plus 6 is 11. So that's 1 over 11 times this. 5, negative 2, 3, 1. And now this is a scalar times a matrix. What's the rule? You take that scalar, hit each entry in your matrix, and here's your actual answer. A inverse is going to be 5 over 11, negative 2 over 11, 3 over 11, and 1 over 11. That is actually A inverse. Does that make sense? If you don't believe me, well, fine. Here. What's A times A inverse? Let's see here. 1, 2, negative 3, 5 times this 5 elevenths, negative 2 elevenths, 3 elevenths, 1 11th. It's square. 2 by 2 times a 2 by 2. The answer is going to be a 2 by 2. Watch this. What is 1 times 5 elevenths plus 2 times 3 elevenths? Well, 1 times 5 elevenths, 5 elevenths. 2 times 3 elevenths is 6 elevenths. 5 elevenths and 6 elevenths is 11 elevenths. Makes it more. Row by column. 1 times negative 2 elevenths. 2 times positive 1 eleventh. So 1 times negative 2 elevenths is negative 2 elevenths. 2 times 1 eleventh is 2 elevenths. Negative 2 elevenths plus 2 elevenths is 0. Negative 3 times 5 elevenths is negative 15 elevenths. 5 times 3 elevenths is positive 15 elevenths. Negative 15 elevenths plus positive 15 elevenths is 0. And then second row, second column. Negative 3 times negative 2 elevenths is a positive 6 elevenths. 5 times 1 elevenths is 5 elevenths. 6 elevenths and 5 elevenths is 11 elevenths, which is 1. And there is your identity 2 by 2. Does that make sense? I mean, it's not 2 by 2, not too bad, but you have to get the pattern. It's 1 over AD minus BC, 1 by the main diagonal minus the off diagonal, 1 over that times main diagonal, switch the positions, the off diagonal, negate the signs. There's a pattern for this, but you need to know the pattern because you want these inverses. This is special, 2 by 2. What happens when you get the old 3 by 3s, 4 by 4s, and 27 by 27s and stuff, okay? So let me show you on that. So, another definition here. Don't worry, I'm about to do one in just a second, but I want to get these definitions down and stuff. All right. Given A is a 2 by 2 matrix, and again, A, B, C, D, then A inverse, A is invertible. And what is another word for invertible? Oh, good. Non-singular. When would this guy be invertible? Remember that little formula, 1 over B minus A? The only way you can't be invertible is 1 over that AD minus BC better be equal to 0, because 1 divided by 0 does not exist. So the only way that happens is if that A times D minus B times C, if that's equal to 0, then that's when you get that non-invertible singular case. Does that make sense? So, that right there tells me A times D minus B times C. If that cross does equal 0, then you got yourself a non-invertible singular matrix. Not all matrices are going to be invertible. Okay? So we have to talk about this in terms of this AD minus BC. And for 2 by 2s, this is going to be called the determinant. So definition. A is this matrix 2 by 2, A, B, C, D. Then the determinant of A, denoted DET, because we're math people, don't think too deep, parentheses A, determinant of A, determinant of A is equal to this AD main diagonal minus BC off diagonal. So if the determinant is not equal to 0, then the matrix A will be invertible. However, if the determinant does equal to 0, then A is not invertible. Again, terminology. So you do get these guys here. So again, a classic example here was my 2, -3, 0, 4 case. What is the determinant of A? The determinant of A would be 2 times 4 minus 3, -3 times 0. 2 times 4 minus -3 times 0. 2 times 4 is 8, -3 times 0 is 0, 8 minus 0 is 8. As long as that's not 0, A is going to be invertible. And the answer is, for A inverse, it's 1 over that determinant, 1 over 8, times the main diagonal, switch positions, so this was 2, 4, now it's a 4, 2. The off diagonal, switch their signs. -3 becomes a +3, -0, it's still 0, okay? And then multiply the 1/8 times each term. That gives you 4/8, which is a half, 3/8, 0 times 8 is 0, 2/8 is 1/4, that is actually the answer. Okay? So, keep going. Does that make sense? Again, terminology is the key to this stuff. Now, properties. Properties of inverses. Where are we going with this stuff, and why are we introducing this stuff to you? Of course, to torture you. So, here's how we're going to torture you. We're going to go back and look at matrix equations again. Remember when we started out with matrix equations? It's a great way to start this whole process, but it works off of what we did on chapter 1, test 1 stuff here. So, you were given a matrix equation, A times X equals B. A is going to be square, and A inverse, if it exists, then you can actually solve for X by using the inverse. All right, so again, let me give you a description of what's going on here. Here it is. You got a matrix equation. A times matrix A times X equals B. You got this matrix equation, right? We want to solve for X. Solve for X. Now, here's the deal. A is n by n squared. 1. 2, A inverse exists. Not all matrices have an inverse, so I'm telling you, A inverse exists. Remember what we said. Matrices do not commute. So order matters. So if I'm going to try to solve for A, so AX equals B. Let me give you the modern algebra perspective of this. If I have AX equals B, and if I talk to my daughter who is 12 years old and in the 7th grade here, and I say solve for X, you know what she's going to do? AX equals B, Daddy. I'm going to divide by A, right? And that gets the X by himself. What's the opposite of multiplication? Division. That's what she knows. Excellent. She's been taught by the best. So, she divides both sides by A, and she's going to get X is equal to B over A. You with me? That's correct. The problem is there is no division with matrices. We never define, and we never will define divides. What we have in lieu of divides is, if we want to kill off an A, I got to have an A inverse. The inverse kills off that A. But what side of my equation is my A on? Look, what side of my variable is my A on? It's on the left side. Agreed? So I got to multiply on the left side A inverse. Order matters. But what I do to one side of an equation, I do to the other. You with me? So this cancels. So that leaves me with X is equal to A inverse times B. Does that make sense? And that is going to give me the solution. I'm going to, the A inverse, I either have it or I'm going to have to go discover it, and I multiply the A inverse times B. And A inverse has to be on the left. It cannot be on the right because the A was on the left. A inverse times B ends up being my solution. So we can turn matrix equations into matrix algebra to be able to solve this stuff. That's where we're going with this. Does that make sense? We're trying to say, but you can't divide. Divide does not exist in linear algebra. You can't divide by A, but if it exists, you can multiply by A inverse, and that's going to kill them off. Because what happens here is this. A inverse times A ends up being the identity. And the identity times X equals A inverse times B, but the identity times X, when you multiply by identity on the left or the right, you just get x back again equals A inverse times B, and that's how we get our solution. Does that make sense? The game plan here. So, from that, we have, quote, these properties. So, given that A times X equals B and A inverse exists, then I would multiply by A inverse on both sides. A inverse times A would give me identity, times X is just X. So get X right there. X is equal to A inverse times vector B. And this is going to be the unique solution for any B that is of correct dimension. Now, you, of course, size matters on this stuff. You know, m by n, m by 1, you got to make sure that you can, you know, multiply this stuff together so the dimensions of this stuff matches up. Other properties of inverses, just like with transpose. What is A inverse inverse? If you take A and invert it back again, what are you going to get back? A. So that logically would make sense. A inverse inverse is A. But here's another property. A times B inverse. If you take matrix A and times matrix B, go ahead and multiply those guys together and then invert it. That would be the same thing as taking B, inverting it, times matrix A and inverting it. So when you inverse, just like we did with transpose, you've got to switch them. So A times B inverse is equal to B inverse times A inverse. Provided that A and B are square matrices and they have the same dimension, and of course, the inverse exists. That goes without saying. I mean, if A is non-invertible, just chunk this stuff out the window. But A and B have to both be invertible. That means they both got to be square. Then if you've got A times B inverse, that's equal to B inverse times A inverse. This is the math on how you get that. Why? Well, let me just kind of write it down here. A times B inverse times A times B. Well, the inverse will kill off the original function. That gives you the identity. But if you want to get the identity out of this guy, let me show you. A times B inverse is going to have to be basically B inverse times A inverse, because when you take A, B inverse, you switch them, B inverse times A inverse. B inverse times A inverse times A, B. Then A inverse times A, you put those guys together, that'll give you the identity. Then B inverse times B, that'll give you the identity. So pretty much you get the identity on this guy, which means that AB's got to be the same thing as B multiplied by A inverse B inverse, which means that this AB inverse is the same thing as B inverse times A inverse. So again, it's a logic thing. There's only one inverse. But I can show you, if I multiply AB inverse times AB, I get the identity. But if I multiply AB times the B inverse A inverse on the left, this also gives you that same identity. Since AB is on the right, this means that AB inverse and B inverse A inverse have to be the same thing. And that actually proves what the statement comes from. And then, while we're at it, let's throw some transpose in there. Remember transpose, turning rows into columns and columns into rows. So if you do A transpose and then invert it, it doesn't matter. You can do A inverse and then transpose that, and it'll be the exact same thing. So transpose matrix A and then invert it, or take the inverse and transpose it. They will be the exact same thing. It's another one of our classic properties. Now, so far, I have shown you that you can find the inverse for 2 by 2 matrices. How do you find an inverse for something bigger? But you know, 3 by 3, 4 by 4, 8 by 8, which will be on your next test. How do you find the inverse on this guy? Well, here is the algorithm for finding the inverse. So, I picked on you guys on the first day of class. Let me pick on you again. How many of you guys are computer science majors? Computer engineering, computer science, some talent connected to computers. 95% of you people. Okay, great. What's an algorithm? Come on, this is your life. What's an algorithm? Go ahead and tell me. Something we deal with every day. Yes. What is an algorithm? Step-by-step flow chart of how to do a particular process, usually done in programming, so I can get my program to work. Here it is. Algorithm for finding A inverse. Start with A. First thing I'm going to check has got to be what? N by N. All right. Now, what we're going to do is we're going to augment A with the identity. This is actually brilliant computer scientists, computer science, and how it actually works. Pay attention to this because this is that idea of computers and storage and memory. Let me show you. So to find the inverse, you take A, and not just augment it with, set it equal to what, you augment it with its equivalent identity. So if this A is n by n, augment it with the n by n identity, okay? Then you're going to take this is going to be a very long matrix, okay? So if this A is 3 by 3, the identity is 3 by 3. When you augment it, you're going to end up getting a 3 by 6, right? Then you do reduced row echelon form. Reduced row echelon form. But if A is invertible, when you do reduced row echelon form, you're going to get, basically A is going to turn into the identity because it's going to be invertible, which means when I do reduced row echelon form, I'm going to get 1, sweep down, 0's below it, then a 1, 0's below that, and then sweep up, and sweep down, and sweep up. A will end up turning into the identity. And the identity that was augmented to will actually turn into the inverse. You found the inverse. All that stuff that you're doing, take row 1, multiply by 3, and add to row 2, all that's being stored over here in the identity in terms of the process. And when you keep up with that, that turns into A inverse. So once you got A augmented with I, you do reduced row echelon form. A will turn into the identity. The I will turn into the A inverse, and you just found A inverse, okay? However, if A is some augmented with identity, and you do reduced row echelon form, and you get J, which is not the identity. If it's not going to be the identity, what you're going to end up having is a bunch of row of zeros type thing here on this guy, which means that if this does not turn into the identity, A does not have an inverse. It has to turn into the identity to be able to be invertible. Does that make sense? So, let me give you a quick example here because I'm running out of time. So, A, let's say it's equal to this matrix here. 1, 3, 5, 0, 4, 0, negative 2, 1, 3. Okay? What size matrix is this guy? 3 by 3. Square. Check. Second thing is, our mission here is to find A inverse. Okay? So, finding A inverse on this guy, what I'm going to do is take A and augment with the identity. This would be 1, 3, 5, 0, 4, 0, negative 2, 1, 3, augment 1, 0, 0, 0, 1, 0, 0, 0, 1, the 3 by 3 identity. You with me? Now, here we go. What's my first move? My first move is I'm going to basically take this guy and sweep down, right? So that's going to be 2 times row 1, add it to row 3, replace row 3. This is going to give me 1, 3, 5. Augment 1, 0, 0. Got to do it to the entire row now. 0, 4, 0, 0, 1, 0. Now remember, it's 2 times row 1 added row 3. That would be 0. 2 times 3 is 6 plus 1 is 7. 2 times 5 is 10. Plus 3 is 13. 2 times 1 is 2, plus 0 is 2, 0, 1. That's what I end up getting there, okay? What's my next move? What would you do next? I would make him a pivot. What's that? 1/4 times row 2. 1, 3, 5, augment 1, 0, 0, 0, 1, 0, 0, 1/4, shows up over here, 0, 0, 7, 13, 201. What's my next move? Take this, sweep down and get this guy. So that's what? Negative 7 times row 2, add it to row 3, replace row 3. When I do that, I end up getting this. 1, 3, 5, augment 1, 0, 0, 0, 1, 0, 0, 1/4, 0, and I get 0, 0, 13 to negative 7/4, 1. I went ahead and did the math for you guys on that one. Well, what's my next move? It gets nasty, but I'm sorry, it's what you gotta do. I'm gonna multiply 1/13 times row 3. It's hard for me to avoid fractions on this mess. This will be 1, 3, 5, 0, 1, 0, 0, 0, 1. This will be 1, 0, 0, 0, 1, 4, 0, 2/13, a negative 7, 50-seconds, and 1/13. Okay? And now I've got 2 moves left to make. What are my 2 moves left to make? I want to take this pivot and sweep up. That's negative 5 times row 3, add it to row 1, replace row 1. This is going to give me 0, 0, 1 on the bottom, 2/13, negative 7 over 52, 1/13. This is 0, 1, 0, 0, 1, 4, 0. And now sweeping up, it's going to give you 1, 3, 0, because that's going to kill off that, make it 0. You get awful 3/13, 35 30-seconds, 50 seconds, sorry, 50 seconds, come on, hang on here, and a negative 5/13. And then I got one more move to make. What's my last move? Sweep up, negative 3 times row 2, add it to row 1, replace row 1. I get 1, 0, 0, 0, 1, 0, 0, 0, 1, augmented with, here it comes, 3/13, negative 1/13, negative 5/13, 0, 1, 4, 0, 2/13, negative 7 50-seconds, and 1/13. And as I show you, this turns into that 3x3 identity. This becomes your A inverse. And yes, it is going to be very difficult for me to get you guys to avoid fractions. But this is the algorithm of how you find anything bigger than 2x2. 3x3, 4x4, 102 by 102, you got to do this method in the reduced fractional form. Study hard on this stuff. Plan to give you back the test on Thursday, God willing, and then we'll finish up chapter 2. Also pay attention on Canvas. I've already put your 3rd homework set and your computer homework already up waiting for you guys. Study hard. See you guys then.